Hello again, everyone. Welcome to the second part of Divergent Boundaries. I just want to quickly review some things that I talked about in yesterday's video. I know it went by kind of quickly, so we're going to finish off this idea of divergent boundaries right here, right now. All right? So, as review, quickly, we talked about the definition of a plate boundary, a place where two or more tectonic plates meet. We said there are three types of boundaries: the divergent boundary, the convergent boundary, and the transform boundary. Remember, today this presentation is about the divergent boundaries. And we said that the seafloor is spreading at divergent boundaries, producing mid-ocean ridges with rift valleys at their centers. And I told you, spreading centers, rift valleys, sort of like the same thing, okay? We talked about rift valleys, how they form, how the ridges grow up high above the seafloor. And I showed you this animation that shows the rifting process, the ocean ridge forming process in action. We talked a bit about the world's longest continuous mountain chain, the Mid-Atlantic Ridge, and how it is responsible for today for the continents of North and South America being pushed further away from Africa and Europe. Remember, new crust is being created here at this ridge, and that is propping the Atlantic Ocean open further and further at about a rate of 1 to 2 inches per year. Okay? The last thing that we talked about was this idea of seafloor rock and magnetic reversal. And I told you that the magnetic field of the Earth is produced in the outer core. It's from all the iron sort of swirling around in the outer core. And that produces this magnetic field that you see over here. It sort of looks like a ball of yarn that has been torn at by several cats. But I told you that the Earth's magnetic field is not clean, it's messy. And you can see here, as orange starts at the top and then moves, this is what it looks like. Then we have the reversal. So we know that the magnetic field of the planet is flipping. It flips every so often. But what exactly is the magnetic field? I want to be able to have you learn a little bit more about it and what its importance is before we actually take a look at how we can identify movement of the field in the seafloor rock. Okay, so let's take a couple of minutes here, and I have a short video from NASA that we can watch together.
Above South America, a weak spot in Earth's magnetic field is evolving. Called the South Atlantic Anomaly, this unique region has been expanding for more than a decade, and scientists believe that it's beginning to split into two distinct zones. Now, while this anomaly poses little risk to life here on Earth, it does allow scientists to study the complicated mechanisms behind Earth's magnetism. Around 1,800 miles below the surface, dynamic processes in Earth's liquid iron outer core are continuously generating electrical currents. This accounts for the majority of Earth's magnetic field. But unlike a typical bar magnet with one north and south pole, Earth's magnetism isn't all neat and tidy. If we take a look below the anomaly at the boundaries separating the core and the mantle, we can see the magnetic variations are much stronger. This picture provides a clear link between the anomaly we see in Earth's magnetosphere, its origins deep within Earth's interior, and how it's projected to evolve in the near future. This is important to understand because our planet's magnetic field plays a huge role in shaping the near-Earth environment. In addition to guiding compasses and animal migrations, the magnetic field acts like a shield, repelling charged particles flung from the sun that could be disruptive if they reach the surface. Many of the particles that do slip inside Earth's protective bubble become trapped in large rings of energetic particles called the Van Allen belts, which are held in place by Earth's magnetic field. The inner edge of the innermost belt is about 400 miles from the surface of the Earth at the equator, which keeps particle radiation a safe distance from Earth and orbiting satellites. But because of the offset between Earth's magnetic and rotational poles, and the weakened magnetic field over the South Atlantic anomaly, some energetic particles within the belt do penetrate closer to the Earth's surface. This means that NASA and other space agencies need to account for the extra radiation when low orbit satellites pass through the anomaly. Currently, NASA researchers are using data from satellites along with theoretical models to track the evolution of the South Atlantic anomaly and help prepare for future challenges to managing satellites and humans in space.
All right, so the anomaly right now is not so much my concern as you just getting a basic understanding of how the Earth's magnetic field works. And I think you saw that in this video as you saw the images of the sun just bombarding the Earth with radiation that is deflected by Earth's magnetic field. So it's pretty important, okay? So that being said, how can we tell when the magnetic field flips? Well, something called geomagnetic striping, okay, that's happening on the ocean floor. So as you look at this animation, this would be your mid-ocean ridge or your spreading center or your rift valley, okay? And you see as new crust is produced and it's moved out away from the ridge. Remember, the newest rock would be right along the ridge here and here, with the oldest rock being out here along the edges. Okay, but do you see these different patterns? You see the black stripes, the white stripes, the broken black stripes, the white stripes. All right, these are magnetic minerals. All right, that are cooling as that are being frozen in the rock as it cools. Okay, so you can see here, normally when we look at these kinds of things, the black would indicate a normal magnetic field, and then the white stripes here are when it is reversed, okay, or when a flip occurs. And you can see here all of the confusion sort of that is laid down on the seafloor in the process of magnetic reversal. Okay, so as the planet produces new crust, it gives clues as to what's happening with the magnetic field. All right, if we want to look at more of a professional sort of representation, or you know how a geologist may look at this information, you see here the contours of the ocean floor. All right, and once again you see these black stripes and white stripes. All right, and each, once again, you know, the black stripes would indicate normal polarity, or the you know the normal north and south of the magnetic poles. And then when you see the white stripes, it has undergone a flip. Okay, so we can tell a lot about our magnetic field by taking a look at metal minerals on the seafloor. Pretty neat. So we already talked about divergent boundaries underwater. Now, what happens when divergent boundaries form on land? In this image here, this GIF, you can kind of see this is what we call the Great Rift Valley in Africa. All right, and this is a spot where Eastern Africa is being pulled away from mainland Africa here. So what's going on there? Well, the land tears apart at divergent boundaries as rift valleys form on continents. And that's what we're going to talk about next. So when they're on land, let me move this up just a bit. Rift valleys form on land as hot material rises from deep within the mantle. Get my pointer back. There we go. Let me start over. Rift valleys form on land. As hot material rises from deep within the mantle, heat causes the crust to bulge upward. The crust cracks when it's stretched, allowing magma to rise through and forming volcanoes. As the rift valley grows wider, the continent spreads apart and the valley floor thins and sinks below sea level, which allows water to enter and lakes or seas to form. It sounds like a complicated process, but it's really not. All right, we can break it down into 4 steps, and you're seeing them right here. All right, step A in rift valley formation is you get magma, all right, hot material rising from deep within the mantle, and that heat is going to cause the crust to bulge. All right, you see, we call that upwarping. All right, next, as the crust, remember, this is a boundary and these plates are being pulled apart, okay? So it's just like when you get that first piping hot piece of pizza out of the box when it's delivered, right? You got your extra cheese and everything, and you pull that little slice of pie out of there, and what happens to the cheese when it's hot, right? It doesn't want to break, right? So you stretch it and stretch it. And if you stretch that cheese far enough as it's hot, what's going to happen? It's going to start to sag in the middle, okay? And that's not what happens with cold rock. Cold rock doesn't stretch, all right? So as the plates are pulling apart, what's going to happen to that rock? It's like your cold pizza, your cheese on your cold pizza. You can just break it right off, okay? So all of these blocks form cracks and they tilt. And as the valley floor drops, all right, you see the initial stages of the rift valley forming, all right? The block in the middle here drops down significantly. And you have these sort of plateaus that gradually raise up as the land is pulling apart. Now, the third step in this is if that land drops far enough, a shallow sea may rush in to cover it. This is exactly how the Red Sea formed, all right? If that rift continues to widen, all right, then eventually it can be covered by the ocean and you'll get a mid-ocean ridge starting to form, okay? For our purposes here, though, we would stop at letter C, all right? And sometimes, as what we're seeing in the Great Rift Valley right now, they're about at this stage, okay? And, you know, hundreds of thousands of years into the future, you know, Africa will enter this stage until finally the whole eastern portion pulls away enough that the ocean, the Indian Ocean, can actually rush in and cover it up. So those are your steps to rift valley formation on land. Where is this happening currently on this planet? Well, I told you about Africa's Great Rift Valley. You can see here you have plate being pulled this way, plate being pulled this way, and all through here, you see all of these volcanoes that dot the landscape in East Africa. Okay, this is the Great Rift Valley, and there are a lot of volcanoes and a lot of lakes because the land has dropped so far. Okay, so that's probably the most famous rift valley in the world, Africa's Great Rift Valley. But I told you in yesterday's video we were going to come back to Iceland because Iceland is also being torn apart. As you look here, you see these arrows indicating plate moving this way, plate moving this way, divergent boundary. All right, and you're getting all of this rifting right here on the continent. Essentially, what's happening is Iceland is getting bigger, okay, as it widens. All right, there's a national park that runs along the ridge here, and it's called Thingvellir National Park. So if you had a chance to visit the Thingvellir Valley, you see an image right here of Iceland's Thingvellir Valley. This is one place in the world where you can actually walk. Well, it's not all covered by a shallow stream like this is here, but there are some portions where the rock here, you can actually walk over here and put your hand on the North American plate. Then you could walk to the other side and actually put your hand on the Eurasian plate. All right, both plates right there. Only spot in the world where you can stand and touch both. Pretty cool, right? But that is what's happening in Iceland currently. So one last thing that I want to include in divergent boundaries is this idea of hotspots and how we can use hotspots to track tectonic plate movements. So hotspots are areas where heated rock rises in plumes or thin columns from the mantle. Now, hotspots don't move. They stay stationary. All right. What does move is the plate above it. So if the plate stays over the hot spot for an extended period of time, the rock above it will melt, and in time, a volcano will form at the surface of the plate. The volcano will eventually continue to erupt and erupt until it builds itself up above sea level. And guess what that is? That's an island. All right, an island is nothing more than a large underwater mountain that pokes its head out the top. Okay, so as the Pacific plate moves slowly over a hot spot, the Hawaiian Islands are being built. So the last thing that I want to do is I want to show you here how hotspots work and how we can track plate movements using them.
A hotspot is a localized source of high heat energy that sustains volcanism. It is not an isolated shallow magma reservoir beneath the crust, nor is it a pipe of magma that streams from the outer core. One theory holds that hotspots may begin as a blowtorch-like thermal perturbation in a zone between the liquid outer core and overlying mantle about 2,900 kilometers deep. The thermal plume allows solid, yet mobile mantle to rise very slowly and convect outward. Convection is the process by which heated material rises and cooler material sinks. Although magma may be generated as deep as 1,500 kilometers, individual blobs do not traverse the entire mantle. Let's zoom in to look at the onset of hotspot volcanism beneath a moving plate. As each pocket of melt stalls, its heat is transferred to adjacent rock. This transfer continues to the base of the tectonic plate, where decreased pressure facilitates rock melting. The magma that forms at the base of this plate rises through the plate in a network of cracks and shallow chambers and erupts on the surface. Over hundreds of thousands of years, large volcanoes build on top of the plate. The weight of the volcanoes bends the plate downward. Volcanoes that spent their constructive life over the thermal plume slowly get rafted away on the moving plate, and new volcanoes build in their place. Multiple dikes can feed several volcanoes from separate conduits. The moving plate drags the thermal plume with it. This can explain why volcanoes can erupt again after centuries of quiescence, even after they have moved off the center of the hotspot. However, erosion greatly outpaces volcanism as eruptions wane, and the buoyant effect of the plume diminishes, allowing the volcano to subside.
All right. So imagine this as the Hawaiian Islands. Okay. We'll take a look at the Hawaiian Islands in Google Earth. We'll take a look probably when we get to shield volcanoes. We'll revisit this hotspot idea. All right. And we'll talk about how the hotspot continually punches new islands up through the crust as the tectonic plate above moves. Yellowstone is another volcano where we can track the movement of the North American plate. Okay. We have old, what we call calderas or volcanic craters from ancient blasts of Yellowstone. So it's over a hot spot also. And that's it, folks, for Divergent Boundaries. I hope that you were able to take the information from today and synthesize it a little bit with yesterday's information. If you have any questions about this, we can talk about it in class. All right. We'll see you.